Hello everybody, I'm Akriti Kutyala and welcome back to my channel. We are starting a new series on RCC Design, Reinforced Cement Concrete, where you will not only learn about the manual design process, but also how to model it in Revit. This series is in collaboration with Novatr, a leading platform that helps civil engineers upgrade their skills with industry-focused courses on BIM, Revit and more. Through this series, you'll gain both theoretical knowledge and practical expertise to excel in the field. So stay tuned, it's going to be an exciting journey.
We'll continue with the subject reinforced cement concrete using limit state method. We were discussing the topic design of beams. We'll be referring to the books by Dr. B.C. Punmya and by Dr. Birender Singh. The prerequisites for the subject are IS 456-2000. I prefer if you have it handy. There are two membership plans available on the channel. The first one is the Himalayan Birch, where you can access videos for the subjects fluid mechanics and surveying, and the other membership plan is the Himalayan Oak, where you can access videos for the subjects fluid mechanics, surveying, steel structure design and drawing. So far we've completed numerical problems, a simple problem based on design of RCC beams and another numerical problem based on design of RCC beams where we learned how to cut off tension bars. So continuing with the same topic, we'll be discussing another numerical. Design a simply supported beam with the following data. Clear span of the beam is 6 meters. Superimposed dead load is 28 kilonewton per meter. Live load is 25 kilonewton per meter. We have to use M20 concrete and Fe415 steel. Take nominal cover is equal to 20 mm and bearing on the walls is equal to 800 millimeters. So the given data from this question is live load is 25 kilonewton per meter, superimposed dead load is 28 kilonewton per meter, clear span is 6 meters which can be written as 6000 millimeter, M20 concrete is being asked to use, therefore the FCK value is 20 Newton per millimeter square. Similarly, Fe415 steel is to be used, so Fy will be equal to 415 Newton per millimeter square. Nominal cover is 20 millimeters. We have to convert it into effective cover. So we'll assume an effective cover of 50 millimeters. Now moving on to the first step, dimensions of the beam. So assuming D to be L by 10 to L by 8, we know that L is equal to 6000. This is the clear span, so 6000 millimeters. So we can calculate the range between 6000 upon 10 to 6000 upon 8, which calculates to be equal to 600 mm to 750 mm. We have to choose a value of overall depth of the beam in between this range. So we assume D to be equal to 650 mm. Now we have to assume the value of B, which can be half of D or 2/3 of D, which calculates to be equal to 325 mm to 433 mm. So we have to assume a value in between this range. So assuming it to be equal to 350 mm. Now we have both the dimensions. D is equal to 650 mm and B is equal to 350 mm. And we also have assumed the effective cover, which is equal to 50 mm. So we can calculate the effective depth of the beam, which will be equal to D minus the effective cover. So that will be equal to 650 minus 50, which is equal to 600 mm. So we have the effective depth is equal to 600 mm. Now we can move forward with the next step, effective span of the beam. As per clause 22.2, for simply supported beams or slabs, we have to keep in mind that this effective span should be equal to the center to center distance between the supports, or the clear span plus the effective depth, whichever is the least as per this clause. So we can calculate the first part using clear span plus width of support by 2 plus width of support by 2. Width of the support has been given to us in the question as 800 mm. So substituting the values, we obtain the first part to be equal to 6800 mm or 6.8 meters. Now substituting the values in the second part of the equation, which is clear span plus D, we obtain a value of 6600 millimeters or 6.6 meters. So as per the clause 22.2, we have to take the least of these two values, which is equal to 6.6 meters. So our effective span or L effective is equal to 6.6 meters. Now moving on to the next step, that is self-weight of the beam, which can be calculated simply by using the formula D overall depth into overall breadth into unit length, that is 1 meters, and the unit weight of RCC. The unit weight of RCC can be calculated from clause 19.2.1, which says that for reinforced cement concrete, the value of unit weight of RCC will be equal to 25 kilonewton per meter cube. We have to keep in mind that this length which we have assumed is in meters, so we'll have to use all the other values in the same units. So substituting, we obtain a value of self-weight equal to 5687.5 Newton per meter. So this is the self weight of the beam. We can round it up to 5688 Newton per meter for ease in calculation. Now we can move on to the next step, where we calculate the factored load. We have the values of live load and superimposed dead load given in the question, and we have calculated the value of self weight. The self weight and the superimposed dead load compute to the total value of dead load. They calculate to be equal to the sum of these two values. So substituting these values, we get 88,032 Newton per meter. We have to keep in mind that in the question these values are given in kilonewton per meter, but the self weight has been calculated in Newton per meter, so we have to first convert them into the same units and then only addition will be possible. So we've calculated the factored load. Moving on to the next step, ultimate maximum bending moment. So we can calculate the maximum bending moment as WU L effective square upon 8. Substituting the values, we have the value of mu equal to 479,334.24 Newton per meter. So we can convert it into a more usable form, which is equal to 479.3 into 10 to the power 6 kilonewton per millimeter. So we have converted Newton into kilonewton and meter into millimeter. We also have to keep in mind that because this value is in Newton per meter, we will take the value of L effective in the terms of meters only. So this value of mu will be equal to mu limiting, because we always design a balanced section as we have seen in the previous questions. I'm sorry for the units, it will be Newton meter and kilonewton millimeter. Pardon me for this. So now designing a balanced section, we refer to an Engg G, where mu limiting is equal to 0.36 xu max by d into 1 minus 0.42 xu max by d Vd square FCK. And from clause 38.1, we know for FE415 or for FY415, we have a value of xu max by d equal to 0.48. So substituting this value here, we get a new equation which is 0.138 FCK BD square. This will be equal to the value of mu which we have calculated previously. So now substituting, we will check for the value of d. While substituting the values, we again have to keep in mind that all the units are similar. Like if this value is in millimeters, then this should also be in millimeters and so on. So this calculates to be equal to 704.4 mm. However, what value have we provided? We have provided, or we have assumed, a value of effective depth equal to 600 mm. So this 600 mm is much less than the required value of 704 mm. Therefore, this section which we have designed so far is not okay, and we will have to redesign. So we will have to go back to the first step. So this is very important. if this value which we had assumed was greater than the value required of 704 mm, then we could have moved on to the next step, but because this value is less, so we have to redesign. So going back to the first step, we will now directly assume a higher value of the overall depth, which is equal to 800 mm. This is also what we are assuming. Why have I chosen 800 mm? Because the required value of D was approximately 704 millimeters. So I am taking a factor of safety and I am adding a 50 mm more. So by this calculation, the effective depth will be equal to 750 mm approximately, and the overall depth can be equal to 800 mm. So I have taken a factor of safety so that this does not fail in the next check. Now B can be assumed to be the same. So I am continuing with the value of B equal to 350 mm only, because we don't have a check for B and this seems to be appropriate. So we'll move forward with these two new values of overall depth equal to 800 mm, overall breadth is equal to 350 mm, and effective depth is equal to 750 mm. We'll recalculate the effective span. So again, from clause 22.2a, we have calculated this value with the new value of effective depth, and we will take the least value, which is equal to 6.75. So L effective, now our revised L effective, 6.75 mm. So moving on to the next step, self-weight of the beam. Again, we'll be using the same formula used before. We obtain the value of the self-weight of the beam equal to 7,000 Newton per meter. The steps which I am following here are exactly same as followed before the section failed. So if you can see that the value of self-weight has increased from around 56,000 Newton per meter to 7,000 Newton per meter, because we have increased the overall depth of the beam. Now calculating the factored load, live load and dead load can be calculated as done before, and we obtain a value of factored load equal to 90,000 Newton per meter. So using this value, we can again calculate the maximum bending moment for the beam, which on substituting the latest value gives us a value of 512,578 into 10 to the power 3 Newton millimeters, or we can simply write 512.6 into 10 to the power 6 Newton millimeter. We know that the beam is designed as a balanced section, so mu will be equal to mu limiting as before. From annexure G and clause 38.1, we will calculate the value of mu limiting. Now, since we know that mu limiting is equal to mu, we will again use this formula to check for the value of effective depth which we have provided. So rearranging this equation, from here the value of D required calculates to be equal to 728 mm. However, we have provided a value of 750 mm for D. So hence we are safe. Now this is important because earlier when our section failed, we took again, rather than taking the value of 704 exactly, we increased the value by 50 mm approximately so that we could satisfy this check. This is the reason, rather than taking 700 as the new value, I assumed the value to be equal to 750 mm and the overall depth to be equal to 800 mm. You can assume a higher value also if you want to avoid failure at this stage. However, it becomes more economical if we keep this additional value to be low, not very high. So the new values or the new dimensions of the beam are: overall depth is 800 mm, the effective depth is 750 mm, and the width is 350 mm. The next step is calculating the area of tension steel. Again, we will be referring to annexure G, where we'll calculate this AST using this given formula. XU by D, because this is a balanced section, so we will be taking XU is equal to XU max, and XU by D can be substituted as 0.48 from clause 38.1. 1. So substituting these values, we obtain a value of AST equal to 2512.67 millimeter square. So this is the area of steel required for this given load or given moment which we've calculated. However, we have to convert it into number of bars. So number of bars will be equal to area of the steel divided by the area of one bar. So first we'll have to assume what value of bars which what is the diameter of bars which we are going to provide. So assuming that we are providing 25 diameter bars, we obtain a value of 5.11 bars. Now we know that we won't be able to provide this in decimal, so we'll have to provide 6 bars. However, if you see that the difference between 5.11 and 6 bars is significant and we are wasting a lot of steel here, so to make it more economical, we will be providing two different diameters. We can split this area of steel into 25 diameter bars and 20 diameter bars, so that this difference which will be here because of increasing this 5.11 to 6 bars can be reduced. So what we'll do is we are just assuming that let's provide 4 25 bars and 2 20 bars, and let's see if we can satisfy this value of AST required. So this combination yields a value of AST equal to 2591.79 millimeters square, which is very close or close enough to the value of AST required. So this combination is good for us, and we'll be providing this combination, and this will be the AST provided. Keep in mind that we might have to carry out this calculations 1 or 2 times to get the right number of bars, so that the AST provided and the AST required are close enough to each other. Now we have to check this value for the minimum and maximum value of AST. So according to clause 26.5.1.1, the minimum value of AST should satisfy this equation. So substituting the values here, this calculates to be equal to 537.65 millimeter square, which is less than the AST provided. Hence this is okay. So now we can check for the maximum value using clause, using the same clause, just a B part. So clause 26.5.1.1b. It is important that you always mention the clause which you are referring to while solving an RCC or steel design question, as it will help you to fetch full marks in the LSM exams and also the competitive exams which are subjective in nature, like ES or any other state exam. So AST maximum calculates to be equal to 11,200 millimeters square, which is again greater than the AST provided. So our value of AST provided is within the range of AST maximum and AST minimum, is shown here. So now what we have to do is we have to provide these bars and calculate the spacing between these bars. So the beam will look something like this, assuming that these two bars in the middle are 20 diameter bars and the rest are 25 diameter bars. So what we have to do is we have to calculate this spacing between these bars, this effective spacing which is there between these bars. So it will be according to clause 26.3.2. So first of all, we'll calculate the spacing. So let's understand how did we come up with this. This is the entire width of the beam. Then we have to deduct the value of the effective cover, the side covers. So these are minus twice of effective cover. Then because we are already at the center of this 25 diameter bar, so we can see that we have 1, 2, half of this bar, half of this bar. So in all 3 25 diameter bars, and the remaining are 2 20 diameter bars. So this is the space which is left in between. This will not be the effective space, however, this will be the clear space between the bars. This is the space which we are talking about, the clear space in between the bars. So how many spaces are there? 1, 2, 3, 4 and 5. So we have divided this entire equation by 5. So calculating, we get this individual space is equal to 27 mm. Now we'll check it with this clause. This says that the space should be equal to the greatest diameter. So this should be greater than 5 max. So 5 max is 25 mm. So hence it is okay. 25. It is greater than 25 mm. Next, the clause says that it should be 5 mm greater than the aggregate size, the largest aggregate size, so that is 20 mm. So plus 5, 25 mm. So this value of 27 mm satisfies clause 26.3.2, and if you have less time in the exam, you can move forward with this calculation and provide the bars in this arrangement. However, for the sake of understanding and to make it easier for the laborers, we will try another arrangement here, in which we'll provide a spacer bar at 1 meters interval center to center. So what is a spacer bar? A spacer bar is simply a bar which is provided so that we can provide the given bars or the required bars in 2 layers, and to maintain that distance between them, that constant distance between this 20 mm diameter bar and this 25 mm diameter bar, we provide a horizontal bar called the spacer bar, and it will be provided after every 1 meter. So let's say this is the beam. These are the lower bars which are provided. So we will provide a spacer bar here. A spacer bar here. Then after an interval of 1 meter, there will be another spacer bar, and then there will be another spacer bar after an interval of 1 meter. Now above this spacer bar, we can easily provide the 20 mm diameter beam. So we can keep it here. So this is how the spacer bar works. Now when we provide this arrangement, the effective depth will be till the center of the spacer bar. So we have to go up to the center of the spacer bar from the top fiber, and that depth will be the effective depth D. So this, if we assume that till the middle of the spacer bar from the bottom fiber the distance is 70 mm. Earlier we were assuming this to be 50 mm, but we have increased it slightly by 70 mm, by 20 mm, and made it equal to 70 mm. So now the effective depth will be recalculated, and it will be equal to 800 minus 70, which is equal to 730 mm. We have to keep in mind that the required depth was 728 mm, and this depth which we have recalculated is again greater than this 728 mm. This cannot be less than 728 mm. However, to ease our question, or to save time, we will not be calculating the entire thing again, because we assumed 750 mm and we did our calculations, and we'll move forward with those calculations. However, while detailing, we'll show that this depth is 730 mm, and now this step onwards, we'll assume the value of the effective depth to be equal to 730 mm only. Since we have provided this new arrangement, the spacing between, the clear spacing between the bars has also changed. It is being provided in 2 different layers. So we will again have to calculate the horizontal spacing between the bars. This is significant only in the lower row. So in the 25 mm row, so this will be equal to B minus 2C effective minus 3 times of 5 max, or 5 1, divided by 3. So 1, 2 and 3. This calculates to be equal to 58.3 mm, which satisfy the value of 25 mm from the maximum diameter bar, and the nominal maximum size of coarse aggregate plus 5 mm is also equal to 25 mm. So this is being satisfied here. We have to keep in mind that if there is less time, or if the question is not specifically asking us to provide a spacer bar and this check satisfies, then we do not have to go on and carry out all these calculations and waste time in the question, especially in the exam. However, if the question specifically specifies that we have to use a spacer bar, or this condition fails, let's say this value was not 27 mm and it was 24 mm, then we had no other choice but to move forward with this sort of arrangement. So it is a call while we are carrying out the calculations. Similarly, until and unless the question mentions that you have to provide bent up bars, which we'll cover in the next question, or you have to curtail bars, or cut off bars, until and unless it has been specifically mentioned, we will not provide these and waste time, because these are time consuming calculations, and as it is, we are running out of time in the exam. So even in this question, we won't be providing any of these arrangements, because the question has not specifically mentioned us to provide them. Therefore, we'll continue with the same arrangement throughout the L section of the beam. Now moving on to the next step, that is shear. So for shear, first of all, we have to calculate the critical section of the beam. The critical section is, as per clause 26.6.2, it is at distance d from the face of the support. We have done this in the previous two questions. And what we have to do is we have to calculate the factored shear force at the center of the support. So this is the center of the support. We'll calculate this factored shear force using the simple formula WU L effective by 2, which calculates to be equal to 297108 Newton. So we have the value of VUR, that is the factored shear force at the center of the support. Now we have to calculate the value of the shear force at this critical section C, the factored shear force at this critical section C. So before that, we need to calculate this value of X. What is X? X is simply the distance of the critical section from the center of the beam. So we know that the critical section is at a distance of D, effective depth D, from the face of the support. So we can simply calculate the value of X using the formula L effective by 2, because this is till the center of the beam, then minus the half the width of the support, because we have to go till the center of the reaction, and this effective depth D. So calculating, we obtain X is equal to 2245 mm from the center, which can be simply written as 2.245 meters from the center, or simply 2.25 meters. So the value of X, that is the value of or distance of critical section from the center of the beam, is equal to 2.25 meters. We can calculate the value of VUC from similar triangle ABO and CDO. So VUC can be calculated from rearranging this equation obtained from similar triangles. So VUC is equal to 198072 Newton. So we have the value of the shear force at the critical section from these similar triangles. Why was this value of shear force at critical section necessary? Because as per clause 40.1, we have to calculate the nominal shear stress, and for the nominal shear stress, the formula is VUCR upon BD. So this VUCR will be utilized here. Now we have to keep in mind that we are using the new value of effective depth, that is 730 mm. So this calculates to be equal to 0.775 Newton per millimeter square. So the nominal shear stress is 0.775 Newton per millimeter square. Checking it with table 20. Table 20 gives us the value of maximum shear stress for concrete, which the concrete can take. For M20, the value is 2.8 Newton per mm. So now we have this value less than, the value of nominal shear stress is less than the value of the maximum shear stress which is permissible by code in table 20. So this is okay. Moving on from table 19, we have to calculate the design shear strength of concrete. How much shear can concrete resist? So to calculate tau C, first we will have to calculate the percentage of steel which we have provided the value of P. So to calculate the value of P, we need the value of provided AST which we have computed as 2500 591.79 millimeters square in the previous steps. So calculating P, we obtain a value of 1.0144%. So if we see, we have a value of 0.62 corresponding to 1% for M20 concrete, and the next value is 1.25, and the corresponding value of tau C for M20 concrete is 0.67. Since we are very close to 1%, and to save time, we can approximate it equal to 1. If you have ample time, you can interpolate between these two values and calculate a value close that of tau C from interpolation. So assuming tau C from P is equal to 1%, we get tau C is equal to 0.62 Newton per mm square. From the previous steps, we know tau V is equal to 0.77 Newton per mm square. This is the nominal shear stress. This is the shear stress which concrete can resist. So for the difference between the two, we will have to provide shear reinforcement in the form of vertical stirrups or bent up bars. So calculating the amount is 0.155 Newton per mm square. So this is the shear stress for which we have to provide shear reinforcement. Since the question does not mention that we have to provide bent up bars, so we will simply be providing vertical stirrups. So first of all, we have assumed that we are going to provide two-legged 8 mm diameter bars, vertical stirrups. So to calculate that, we need to know the shear force corresponding to which we will be providing the vertical stirrups, so that VUS can be calculated from this tau US, the difference between tau V and tau C, into BD. So calculating, we get 39,602.5 Newton. So this is the value corresponding to which we have to provide shear resistance in the form of shear reinforcement. So using this equation, or from clause 40.4, we obtain VUS is equal to 0.87 Fy ASVD upon SV, where VUS we have calculated, Fy we know, D we know, ASV is the area of the stirrup which we can calculate from two-legged 8 mm diameter stirrup. So what is remaining is this SV. So rearranging this equation for SV, this SV is the distance which is required as per this calculation of shear force between the stirrups. So calculating, SV computes to be 669.057 mm. So we need to provide a spacing, or the required spacing as per the shear force calculation is 669.057 millimeters. However, we have to provide a check to the minimum shear reinforcement which we are going to provide. So as per clause 26.5.1.6, we have to use this formula for the minimum shear reinforcement, in which we can again calculate the value of SV from here. This is the maximum. If the shear reinforcement is minimum, then the spacing that we can provide here corresponding to the minimum shear reinforcement will be maximum. Now, since we have decided the diameter of the stirrup, and we have also decided that it is going to be a two-legged stirrup, we cannot change this value of ASV, which will again remain 100.53 corresponding to two-legged 8 mm diameter stirrup. So calculating SV max, we obtain a value of 259.26 mm. So this is the SV max which is permitted by clause 26.5.1.6. Now, as per clause 26.5.1.5, this maximum spacing has to be less than 0.75 D where we are using vertical stirrups, or 300 mm, whichever is least. So calculating 547.5 mm and 300 mm. So combining these two clauses, we have to utilize the least value for the maximum spacing permissible between the stirrups. So if we see, this is 259.26 is the minimum value, the least value out of all three. So selecting SV max is equal to 259.26 mm. However, we cannot provide a value of spacing in decimal in the field, so we will provide a value of spacing between the stirrups equal to 250 mm. Why am I taking 250 mm and not rounding it up to 260 mm? Because 259 is the maximum value. I cannot go beyond this value, so I will go to the least or the nearest lower multiple of 10. So the lowest multiple of 10, the lower side, on the lower side, the multiple of 10 is equal to 250 mm. So we will be providing a spacing of 250 mm. Therefore, provide two-legged 8 mm diameter stirrups at the rate of 250 mm center to center. Now we can keep one thing in mind, that we have assumed the diameter of the stirrups to be equal to 8 mm. However, if we want that this minimum or the maximum spacing is greater than 259, we want it to be around 300 mm or so. So we can increase this value. To increase this value, we can increase the diameter of the stirrup. So you can also try it, the calculations with 10 mm diameter stirrups. Like it can be simply provide two-legged 10 mm diameter stirrups, and you can calculate the new spacing, which will be more than the spacing of 250 mm. Now moving on to the next step, we will be calculating or we will be carrying out the check for deflection. This is as per clause 23.2. So if you see that as per clause 23.2.1, we can calculate the maximum vertical deflection limits, and for simply supported, the factor provided is 20. So we can write that L by D, that is the deflection maximum value, is equal to 20, because it is a simply supported beam, into KT, KC and KF, where KT, KC and KF are the modification factors for tension reinforcement, compression reinforcement and for flange and T-beams. We can calculate the value of KT from figure 4 of the code. Here in this case, no compression reinforcement is being provided, therefore the value of Kc will be equal to 1, and because this is a rectangular beam, the value of Kf will also be equal to 1. So I simply need to calculate the value of Kt from figure 4, and I'll obtain the value of L upon D maximum. So from figure 4, we have to first, to identify this modification factor, we have to calculate this percentage of tension reinforcement and the value of Fs. So first we'll calculate the percentage of tension reinforcement as we calculated in the previous step of shear. So percentage of tension reinforcement is equal to 1.0144%. We can approximate it equal to 1%. So we have the value of P is equal to 1%. Now from this formula given in the figure, we have to calculate the value of Fs. So Fs is equal to 0.58 Fy into AST required upon AST provided. From step 6, we have the values of AST required and AST provided. So we can calculate the value of Fs, which is equal to 233.3 Newton per mm square. So now from the value of percentage of tension reinforcement and the value of Fs, we have to calculate the modification factor. If we see 233 will fall somewhere between these two lines of Fs equal to 190 and Fs is equal to 240, and percentage of steel, tension steel equal to 1 lies on this vertical line, this line. So we will be assuming the value such that if this is 240, then somewhere here will be the value 233, and if we interpolate or if we extend this line to the vertical axis, this point will be equal to 1.1 and this will be equal to 1.0. So somewhere in between 1.1 and 1.0 we have this value of 233. This is again an assumption and it might vary when you from person to person. So here I am assuming the value of kt is equal to 1.05, somewhere between 1.0 and 1.1, so 1.05. Now I have the value of kt also, which is equal to 1.05. So I can calculate the value of L upon D max, which is equal to 20 into 1.05, which is 21. Now what is the actual or the provided L by D max, L by D provided can be calculated simply. L is equal to 6750, the L effective value, D is 730 mm. So the ratio calculates to be equal to 9.2. Now this value of 9.2 is less than the maximum permissible value of 21. So I can write L upon D max is greater than L upon D provided, hence this is okay. So the check for deflection turns out to be safe. Now here, because there is a special case where the depth of the beam is greater than 750 mm, so we will have to provide side face reinforcement as per clause 26.5.1.3. So this clause simply says that when the depth of the beam exceeds 750 mm, in our case the depth is equal to 800 mm, so we fall under this category, the total area of such side face reinforcement shall be provided along the two faces. So we have to provide side face reinforcement, and that too along both the faces of the beam. The total area of this reinforcement shall not be less than 0.1% of the web area and shall be equally distributed on the two faces at a spacing not exceeding 300 mm or web thickness, whichever is less. So according to this clause, we will have to provide side face reinforcement. So let's proceed. The side face reinforcement has to be 0.1% of the web. So web area is B into D. 0.1 and this is percent, so divided by 100 we obtain side face reinforcement as per clause 26.5.1.3 as 280 mm square. So now the clause also mentions that we have to provide this side face reinforcement of 1% of web area on both the faces. This is the side face reinforcement depicted in red here, and it should be equally divided. So let's say if I am providing 2 bars on one face of the beam, then I will have to provide 2 bars on the other face of the beam as well, because it should be equally distributed on the two faces. And it also mentions that the spacing between these 2 bars should not be greater than 300 mm or the width B. So now this 280 mm has to be provided in terms of 4 bars, 1, 2, 3, 4. So let's assume a diameter of 12 mm. This calculates to be equal to 452 mm square. Although this value is greater than 280 mm, but we will have to provide to satisfy the rest of the parts of the clause. So we are going to provide 2 bars of 12 mm diameter on each face. Now come to the spacing of these 2 bars. So according to the clause, we have 2 options. One option is the spacing should not be greater than 300 mm, and the other option is that it should not be greater than the value of B. or width of the beam, which is equal to 350 mm in this case. So we have to take the lower value. The lower value is 300 mm. So we will provide 12 to 12 mm bars on each face at 300 mm center to center. So this brings us to the end of the question. Here we will be discussing the detailing. Now if we see closely, this line represents the four 25 mm diameter bars, then this line represents the two 20 mm diameter bars. These in the L section, these bars are the 25 mm spacer bars at a distance of 1 meter center to center. So you can see these are the spacer bars. Then this uppermost line are the two 12 mm diameter anchor bars which we provide. These horizontal lines in between we can see are the two 12 mm diameter bars on each face at 300 mm center to center. Now we have vertical stirrups, two-legged 8 mm stirrups at 250 mm center to center. This is the cross section. Four 25 mm diameter bars separated by a 25 mm spacer bar, then two 20 mm diameter tension bars, two side face 12 mm diameter bars, side face reinforcement on each face. These are the two anchor bars, one 12 mm here, one 12 mm here. The effective depth is 730 mm and the effective cover is 750 mm. The overall depth is 800 mm and the overall width is 350 mm. So this brings us to the end of the question. I hope you liked the lecture. Thank you. Please subscribe the channel and join the membership program. Have a nice day.
Alright, so here is the detail provided by Akriti. We have the simply supported beam clear span of 6 meter, superimposed at load, live load, grades of concrete and steel, and the nominal cover. So all the necessary data are provided. So let's model it in Revit. You can see that I have already modeled two columns. Our beam is resting on it. This is how it will look like in plan view. And if I cut the section from here, I can also see the cross section. It will be easy for us to place rebars from this view. 350 by 800 is something our desired size. Okay, so very first thing that you need to do is to set the cover. For that, you need to go to structure. Under reinforcement, there is an option cover. Now it is asking us to select the element for which we are, adding the cover. I'm selecting the beam, and I want the 20 mm, which is there. If there is no option, then you can also create your own. Okay, the next step is to add the rebar. I'll go to rebar, and here it will enable some of the different shapes of the rebars, as we will be going first with the stirrups. It's two-legged 8 mm stirrups at 250 mm center to center. So this is what our stirrup shape is. The size is 8 mm. The placement is parallel to the work plane, and this is how we can place it. And you can see that our orientation of the angle is changing if I hover the mouse. But if you want, if you can also place it once, and then you can change it by pressing the space bar on your keyboard. Right now we want it at 250 mm center to center, so I'll be selecting the stirrup. Under rebar set, I'll make it fix spacing of 250, and this is how it will look like in 3D. Now we will go with the anchor and the side face reinforcement. We will make sure that these two bars are at 300 mm center to center. So for that, rebar, we'll go with the typical rebar shape. We will choose the size, which is 12 mm, and the placement, which is parallel to the cover. The rebar set 4 number, fixed number for now. I'll be placing it to make sure that these two bars of 300 mm center to center. What I'll be doing, I'll check the spacing of each. So to make it correct, I'll make this 270 from this side and 300 from this side. So as you can see that now it's all equal, right? I'll be deleting it. Now I'll just go to the custom edit rebars, and I don't want this rebar, I can remove it, right? Now this is what I'll be mirroring. I'll go to modify, mirror, and it's done. So our anchor and the side reinforcements are done. To make sure it's 300 mm, we are just checking it. It's 300 mm. Okay. Now we will go with our tension reinforcement of 25 mm bar, structure rebar, change the size 25 mm, and then you can go with the placement parallel to the cover, rebar set fixed number 4, so it will equally divide to 4, right? And then the spacer bar, which is 25 mm at 1 meter center to center. So what I'll be doing, I'll go to structure, rebar, and just change the placement which is parallel to the work plane, not the cover, and it will be like this. Now it's here and we want it to maximum spacing of 1 meter, so it will be equally spaced at 1 meter center to center. And after that, the tension reinforcement of 20 mm. So what I'll do, I'll just copy it and change it to 20. And now I don't want this corner bars, so I'll just edit bars and I'll remove this bar. So this is how your reinforcement will be done, which contains your stirrups, your anchor bars, side reinforcement, the tension reinforcement, and the spacer bars.